Good evening, and thank you all so much for joining us for tonight's David Elder Lecture. These are hosted in partnership with the University of Strathclyde. My name is Nina, I'm the Planetarium Coordinator here at Glasgow Science Centre, and I'll be hosting the live Q&A portion of the lecture. Shortly, I'll be introducing our guest speaker. After watching his lecture, I'm sure you're going to have plenty of questions for him. So please do send those in via the YouTube or Facebook comment box, and my fantastic producer, Yvonne, will make sure that they get to me. So without further ado, I'd like to introduce tonight's speaker. He is Dr. Benjamin Hamlington, who's joining us from NASA's Jet Propulsion Laboratory in Southern California. Good evening, thank you so much for being with us tonight. So just a little bit about you for our viewers, so they kind of know, they can start thinking about questions they might want to ask you. So Dr. Hamilton is a research scientist in the Sea Level and Ice Group at the NASA JPL. He studies global and regional sea level changes with a particular focus on using satellite observations to understand the changes in sea level on a variety of different timescales. He's done work on understanding sea level during the 20th century, comparing historical data to modern observations made by satellites. And he's also interested in how sea level responds to both natural and human-made forces and what this is going to mean for coastal populations both now and in the future. So this interest extends into bridging the gap between scientists and decision makers and the challenge of generating useful scientific information for planning purposes. He's a member of NASA's Ocean Surface Topography and Grace/Grace-FO, is that how you would say that? Science teams?
That's fine, yeah.
Perfect.
Yep.
And is the current team lead of the NASA Sea Level Change Science Team. He's also a member of the United States Interagency Sea Level Task Force and World Climate Research Programme Grand Challenge on Sea Level. So that's quite a lot. We're absolutely delighted you could join us. So what I'm going to do now is just hand over to you so you can start the lecture, because people are definitely here to hear from you rather than from me. So thank you for joining us.
Thanks a lot for the introduction. Let me share my screen here. I know that was a bit of a mouthful to cover. Let me pull this up real quick. Okay. So first of all, I want to thank the organizers of this lecture series for inviting me to speak today. I think it's really cool. I'm halfway around the world in Southern California, being able to speak to you all about some of the work that NASA is doing, why it's relevant, not just for the United States where I am, but also very broadly for global audiences. So as the introduction mentioned, so today I'm going to be talking about using satellites to understand changing sea levels. And I'll start off by talking about exactly why we're interested in changing sea levels, why that matters. I do want to say that, some of you may be familiar with the Jet Propulsion Laboratory. We do build the rovers that then get sent to Mars, but we also do a great deal of Earth science research. And the satellite observations that we use are really key to our understanding of climate change. All right, so just to start out here, I have this little, very simple schematic of sea level rise and why it matters. And this is just a way of showing how sea level has changed from the past to where we are now. So here I'm showing just a simple example of sea level in the past and what actually drives or causes sea level to change. So in this bottom panel here, this blue, we have this mean sea level. So you can kind of treat that as the foundation of sea level. And there's all these other things that sit on top of it, like an envelope of variability of changes that occur at different time scales that sit on top of this foundation. And coastal communities around the world were built with an understanding of where this foundation of sea level, plus that natural variability from tides and winds and other things like that, where that typically pushed sea level at any given time. So there was a safety gap that was considered for these coastal communities. They ensured that they wouldn't see frequent flooding, they wouldn't have a problem. Only in really extreme cases would you have flooding. The difference now is that this foundation is increased. So now in yellow there at the bottom, we have mean sea level plus sea level rise associated with climate change and global warming. So this safety gap, which was previously really big, is now very small. So all these different processes, these natural processes that happened in the past that didn't cause flooding now become a serious problem. And you also have what I'm calling here land subsidence. So as the ocean is moving up in some locations, you also have the land moving down, and this can really serve to make these problems worse that we're seeing with sea level rise. And it's important to understand like how the scales on which these processes vary, because that really is key in our observations that NASA uses to understand sea level rise and climate change. So you have these local factors that vary a great deal from location to location around the world. So these tides, waves, and winds, very local processes. You have these regional scale signals. So some of you may be familiar with El Nino. That's a big one that affects us here in California. But you have other types of natural variability that happens in other parts of the world and other parts of the ocean. And then you have these big global processes. So this is the warming of the ice sheets, the thermal expansion of the ocean, which I'm going to talk about a lot in this presentation. But these things combine at any given time to really drive sea level and basically your threat and vulnerability to flooding. And just to be clear, I'm going to focus on 3 specific subjects. I'm going to start out by talking about these global processes and how we measure them, the regional processes, so how we start to get some variability in these global rates of sea level rise we're seeing, and then also just touching very briefly on subsidence and why that matters. All right, so why is sea level rise going up globally? So why is sea level rising globally? And there's really 2 reasons for this, and I'm sure a lot of you are very familiar with this. So the biggest one is the ocean is warming. So as the ocean warms, that water expands. So we simply call this thermal expansion, and that causes sea level to rise on these very big global scales. The other main factor is that ice on land is melting, and that meltwater goes into the ocean. So when these ice sheets, the land and the area around these ice sheets warms up, the ice sheets melt, that water has to go somewhere, and in most cases, it goes into the ocean. So this is true of the 2 big ice sheets in Greenland and Antarctica, but also mountain glaciers that are present around the world. That ice melts, and then it has to go. It usually ends up in the ocean. That causes sea level to increase also. And if we're talking about understanding how sea level may change in the future, it's really important to understand these 2 processes really well. And that's where the NASA observations come in and what I want to talk to you today about. So we measure ice, thermal expansion, and what I'm calling total sea level separately. And we can basically assess this equation with our observations. How well does the combination of the ice contribution to sea level rise, the thermal expansion contribution to sea level rise, how well does that combination add up to what we're calling total sea level, which we measure with a particular satellite? So we can assess how well we understand these processes that are causing climate to change. So I'm going to go through each one of these different factors individually, talk about the satellites, how they work a little bit, how they make that measurement, how good that measurement is, and what we can understand from it. And I want to start out by focusing on what I'm calling total sea level and satellite altimeters. So we're using satellites, they're known as satellite altimeters using radar technology to measure total sea level. So before I get into that specific satellite technology, I think it's important to understand, how do we measure global sea level change in the past? So for the last century, tide gauges have really been the predominant way that we've measured sea level change along the world's coastlines. So that middle panel there, I'm showing the tide gauge in San Francisco, not too far from where I am. On the right is a little schematic of how a tide gauge works. It's important to note that tide gauges have to be located and attached to land. So those tide gauges measure what we call relative sea level. It's the change of the ocean relative to land. So that's where that subsidence starts to become a factor. These tide gauges do measure the effect of subsidence. If land is going up or down, that's going to affect the measurement you're making in these tide gauges. But a really key piece here, this bottom panel, if we're trying to measure global sea level, it's very difficult with the tide gauges that we have available. So if you look at that bottom panel, those red dots, each one of those is a tide gauge that is available to us over the course of the 20th century. And you can see that there's a lot of gaps, right? So if you don't have an island, if you have open ocean, you're not going to have a tide gauge. There is a bias towards the northern hemisphere. So some of the more heavily populated areas over the course of the 20th century, more developed areas, they typically have the tide gauges. So we have this hemispheric bias as well in these tide gauges. So if I want to take this set of data and try to estimate global mean sea level, so what the global average sea level change, it's very difficult. I'm just missing observations in a lot of parts of the ocean. All right, so if we shift gears here, and now we have satellites. So over the past roughly 3 decades, so since 1992, we've had these satellite altimeters on flying around the ocean, making measurements of sea level rise, very broad scale. So we don't have these gaps, and I'll show that in just a second. But we have this continuous measurement with near global coverage. And when I say continuous, it hasn't been one satellite flying from 1992 to present. We've had a series of satellites that we can kind of stack up. They've always had overlap and really try to make this continuous record of sea level change. The principle that we use to measure sea level with these satellite altimeters is really very easy. So, or pretty straightforward. The actual details of it are a little more complex. It's a difficult engineering problem, but it's really not that different than, say, a policeman on the highway who's making a measurement of how fast you're going. So these satellites send a radar pulse from the satellite down to the surface of the ocean. This pulse, radar pulse, bounces off the surface of the ocean and travels back to the satellite. So if we can measure the time it takes very accurately from that pulse to get from the satellite to the ocean and back, and we know very accurately where that satellite is up on orbit, we can actually get a really good measurement of what we're calling sea surface height or sea level. And the accuracy of these satellite measurements is really incredible. So we can get an accurate measurement down to about 2 centimeters of sea surface height, up from hundreds of kilometers up on space. So this is a really powerful instrument that we can use to understand sea level on these global scales. I'm going to show you a couple slides and or a couple videos in just a minute about how exactly these observations are taken, and then how we can stack them up to make this global record. All right, so here, this is the Sentinel-6 satellite. This was launched last year. This is a joint collaboration between NASA and the European Space Agency. So those two agencies came together to build the satellite. There's a long history of doing that for these satellite altimeters, but this is the one that was most recently launched. It does look a little bit like a house. That is not intentional, wasn't intentional design. It's just basically how the most efficient setup here. But here we can get a little idea of how this satellite is measuring. So it's orbiting around the Earth. Every 10 days, we get a complete view of the global ocean. So it has a repeat orbit of 10 days. And you can see that it's bouncing this radar pulse directly beneath it at any given time. And it's making that measurement. And you start to build these measurements up and you start to fill in these gaps. So you saw previously that tie gauge slide. We had all these different gaps there. I'll show this one more time. We had all those different gaps, but now with the satellites, we can start to fill in a whole bunch of those gaps. And this one signal in particular, this is a really big El Nino that we're kind of showing a schematic of here. This is a really big signal in the Pacific Ocean. So you have this grid that gets overlaid on the surface of the ocean that the satellite repeats every 10 days. Just to show this in a slightly different way. Okay, so this is, here I'm showing the data that we're collecting starting in 1992 and coming up to the present. So you can see that ground track, but important feature here that I want to start to point to, I'm not going to show the entirety of this video, is how much is going on in the ocean as these measurements are being made, right? So this is the ground track. You can see occasionally the satellite has some problems and that ground track goes in and out or adjusts, but you can see all these different features happen in the ocean. So the ocean is not anywhere close to a bathtub. There's all these different signals going on. It's not just going up and down constantly. There's a lot of regional variability that we can see with these satellites that were previously very difficult to see with the tie gauges on their own. And you can see that El Nino there in 1997, 98. So we have this complete record from 1992 on up through the present. Sentinel-6 is up there now making measurements, and we're collecting the data. All right, so with this global data, so at any given 10-day time period, we can take all that data around the globe and we can average it together. And we generate what we call global mean sea level. Okay, so this is the global average rate of sea level rise. The sea level rise at any other location on Earth is probably not going to be equal to this, but this gives us a really good measure of how sea level is changing globally, and then we can then connect that to climate change, which is a global process, right? So it's warming the Earth globally, it's melting ice, it's causing the ocean to warm and expand. So we can make this measurement, and we end up finding from 1992 to present, the rate of global mean sea level rise is about 3 millimeters per year. And admittedly, that doesn't sound like a lot, right? 3 millimeters is a very small amount over the course of a year. But you have to consider that this has been happening over the course of now 30 years. And this is going to continue to increase in rate in the future. So we expect to see an acceleration. The other important feature here that this rate is really quite linear, right? It's pretty flat. There's not a whole lot of ups and downs. It's very conclusive evidence that sea level is going up, that sea level is rising, that we have from these satellites. And I do just want to note, to circle back here to this one particular point, that we do have this really nice long record of these satellite altimeters. It's a huge engineering and policy feat to be able to have this continuous record with overlap between each of these missions. So here I'm actually showing on the left the different missions that we've launched. So starting with Topex Poseidon back in 1992, on up through Sentinel-6A. The full name is Sentinel-6A Michael Freilich, named after one of the directors here at NASA. But we have this nice stack. We have additional altimeters that are being launched in the future. So the next one is planned for 2025, the Sentinel 6B satellite altimeter. So we have this nice long record, this 30-year record, which is hugely beneficial for our understanding of sea level change. So why is this long record so important? So one reason is that it provides, the longer our record is, the better we can understand the processes that are causing sea level to change. So here, I previously said it's really difficult to measure global mean sea level from tie gauges alone. This is an effort to actually try to do that. So this blue line here is global mean sea level assessed from those tie gauges going back to 1900. And I'm not showing uncertainty on this, but your uncertainty is actually quite large as you go back to 1900 on any individual measurement. And I've also overlaid the satellite data on top of this tie gauge record. But we can see in the past that global mean sea level and the rate of global mean sea level has varied at different time periods. So if you look at that time period roughly from 1950 to say 1980, global mean sea level was actually pretty flat, right? Sea level was not going up that much. But we can actually understand why this was the case. So it wasn't because of a lack of climate change, anything like that. It was actually because there was a huge increase in the number of dam projects around Earth. So the same way that when ice melts, it goes into the ocean, if we are impounding or keeping water on land through these dam projects, on a big enough scale, that can actually affect global mean sea level. So with these records, we can start to put into context the rise that we've seen now. If the satellite record continues to increase, we can see any of these changes that are occurring and try to understand them. So it's really important that we make these global assessments. Apologies if you can hear the dog barking in the background. I am working from home with a couple dogs. Okay, so we've covered total sea level, focused on altimetry. Now I'm going to shift gears to another one of these satellites. So this is measuring ice, and this is the GRACE, where there are two satellites, GRACE and then GRACE follow-on. That FO stands for follow-on. Nothing really more exciting than that. But I want to cover exactly how these satellites are measuring ice change here on Earth. Okay, so GRACE stands for the Gravity Recovery and Climate Experiment. So GRACE actually has two satellites, and GRACE follow-on has two separate satellites. And what these satellites do is measure gravity changes on Earth. And actually, one of the main ways that gravity changes here on Earth is the movement of water around the Earth. So some of that movement can be ice melting and then going into the ocean. The global water cycle is really well measured by these GRACE satellites. So basically the movement of water from land to ocean at any given time, these satellites see that as well. But for the interest of this talk, I'm really going to be focusing on what these satellites can tell us about how much ice is being lost, where that ice is coming from. All right, so the measurement principle of these GRACE satellites is really interesting. So the only measurement they're making is the distance between those two satellites, right? So at any given time, they're just measuring the distance between these two satellites. And as these satellites orbit around the Earth, they're constantly changing the distance between them. Okay, so here on the right, I have a little schematic of that before I show a video. So I think these two things combined hopefully will give an indication of how this is working. But if we look at that top panel on the figure on the right, that first satellite is moving towards something very massive here on Earth. So it's a mountain with some ice on top of it in this case. So that first satellite, as it gets closer to it, the gravitational pull of that big mass pulls that first satellite towards it. And you can see in that second panel that there's this increased separation between the two satellites. Now in that third panel, as the first satellite passes over that mass, it gets pulled back towards it and the other one gets pulled towards it. So again, these two start to close in distance to each other. So that gap closes. And that's what you can see in this bottom panel. You've kind of returned to where you were in the first one, right? So there's a constant interplay of these satellites moving back and forth. From that distance measurement, we can then infer the actual change in mass or change in gravity here on Earth with some, I don't want to make it sound like an easy process, but with some equations and algorithms, we can make that computation. So I have a video that shows this. So you can see what these look like. It was noted in a previous presentation that these also look like little houses. Again, that's not intentional. A lot of our satellites don't look like that, but these two particular ones do. So you can see that as these satellites are flying over Earth, that separation changes. So they're flying over in a mountain range. Now you can see that separation. So this is another image here. That's not a tether. That's basically a measurement being made between those two satellites. So they're not attached to each other. But you can see as it flies over these mountains, these hills, the first one gets pulled towards it, and there's this constant dance between the two satellites. All right, so what do these satellites actually show us? All right, so the first one here, these are measurements from GRACE or actually I think just from GRACE, focusing on the Greenland ice sheet. So as this satellite flies over, it's making measurements of the Greenland ice sheet. We can stack these up over time, and we can really understand not just how much ice is being lost from Greenland, but where that ice is actually being lost. So this is just a schematic. We're starting out here in 2002. So this is mass loss. So that's basically how much ice is being lost. If I were to look at this on the ocean side of things, it would be the opposite direction. We'd be adding mass to the ocean as a result of this. So you can see in a lot of these different areas, Greenland's losing a great deal of ice over this time period. Again, something to note there on the right, it's a very definitive decrease, right? So there's very little ambiguity and how much or whether or not Greenland was losing ice. We know it is very well. We know that rate very well. And I can show the comparable one here for, let me see, for Antarctica. So this is the Antarctic Ice Sheet. There it is. It's a little more complex here because parts of the Antarctic Ice Sheet are actually have been gaining ice in some locations, but the overall loss has been, or the overall ice sheet has been losing mass over this time period. And here we have appended the GRACE follow-on measurements that started in 2018. One note, unlike the altimetry missions, there was a slight gap between these GRACE and GRACE follow-on satellites, so we didn't have the overlap, which would have been very helpful. But here you can see that West Antarctic ice sheet is particularly problematic in terms of how much mass it's losing. Okay, so if we take these measurements from GRACE, and similar to what we did with the altimetry, we have these measurements everywhere across the globe. We can average all of those together. All right, so the contribution of sea level change from this ice mass loss is about 2.1 millimeters per year. So I said previously it was about 3 millimeters per year from altimetry. So we can assess from these satellites that over the past decade plus, about 2/3 of that global sea level rise is coming from ice mass loss. All right, so if we revisit this equation, we have one last factor to talk about. This is the thermal expansion from the Argo profiling floats. These are not satellites. These are actually in situ observations and not a specific NASA observation, but they do kind of complete this assessment here. So just doing the math in our head, we have about 2 millimeters per year from ice. We have 3 millimeters per year from altimetry total sea level. So our expectation for Argo would be about 1 millimeters per year if this were to work out. All right, so these Argo profiling floats, there's a whole bunch of them in the ocean, about 4,000 at any given time. And what they do is they basically travel around with the winds and the currents. They're free floating, but they drift for about, it says here, drift for about 9 days. And then on that 10th day, they descend to a depth of about 2,000 meters, and then they rise to the surface. So as they're rising to the surface, they're measuring salinity and temperature along that water column. And from those measurements, we can then assess what we call thermosteric, or the thermal expansion component of sea level rise actually is. So we can get really good estimates from these Argo profiling floats around the globe. We can average all these together. I don't have any fancy videos to show of a Argo float drifting in the ocean, but if we take those observations that are in global scale, this experiment, these observations started about 2005. So over that time period, we're looking at about 1 millimeter per year of sea level rise. So again, I had already kind of laid it out, but if we revisit this, you can see that what we're calling this global sea level budget does close, right? So we have 2/3 from ice, 1/3 from thermal expansion, and we know from the altimetry that this all kind of works out. So this initially might not seem like a big deal, but it really is for a couple of reasons. One, it's a really good test of how well our observation systems are doing. As scientists, we think we understand the processes that are causing global sea level to change. This is a really good set of independent measurements to actually verify that. The other reason this is very important is as we start to think about projecting sea level into the future, it's really key that we understand the processes now. So these satellites and the measurements that are taken with them, I've kind of assessed them in global scales, but they actually provide really rich regional information to allow us why sea level is changing, why we're getting this global contribution, and where it's coming from. And then importantly, how it varies regionally. Okay, so and that's where I want to jump to now. Oh, actually, yeah. So this is the example. Forgot about the slide. This is the example of showing the budget closure. It does look a little busy here, but I think the key point, that yellow line is the combination of Grace and Argo, and then the blue line is what we have from Altimetry. So this budget closes over that time period. So it's really just reflecting what I just said. All right. So again, I mentioned that up to this point, I've really just been talking about these satellite observations and how they inform us about these global mean average scales. But we can look at the regional variability. And one of the previous videos I showed did give some indication of this. But I want to show a different version of this. And basically, this is the sea level change as measured by satellite altimetry from 1992 on up to present. Oh, let me go back. Okay. So again, the important thing here to understand is how rough the ocean is, how much is going on. We call this the topography, the surface topography of the ocean. There's these short features that happen over the course of a year. There's these longer processes that happen over the course of a couple years. And then there's even longer process beyond that, right? So there's all these different time scales of variability. And if you note that scale, so that scale down there at the bottom goes. So these are big contributions and big shifts that happen on a year-to-year basis. So if we're talking about climate change and the effects of sea level rise at any time in the future, it's not just that foundation of sea level, going back to that very first slide, that we're concerned about. It's also how the natural variability combines with that, that foundation of sea level. So how the up and downs that occur naturally can potentially drive flooding in the future. So now at each of these points on this map, on this video, I can actually generate a time series with the altimetry, and I can estimate the rate of sea level rise at an individual location. And that's what this map is showing. So that figure down there on the right, or that color bar is very difficult to see, I know, but it actually goes from negative 15 centimeters to 15 centimeters. So this is the amount of sea level change we've seen during the satellite altimetry record, from negative 15 centimeters to 15 centimeters. And again, this is from 1992 to present. So you can see that a single global metric is not really that useful here, right? So that 3 millimeters per year is not expressed evenly across the globe. Again, I mentioned the Earth is not a bathtub, it varies, things change. So we have this regional variability in sea level rise that really matters. If you look at hopefully you can see my cursor here, but if you look at the coast of California, you can see that during the satellite record, we actually have not seen that much sea level rise, right? This is associated with some of these shorter term factors that are contributing. But if you look at the other coast, so say the east coast of the United States, we've seen very high rates of sea level rise over this time period. And there's a number of reasons for this that we can, again, try to understand with these observations that we have available to us. All right, so as I mentioned already, sea level changes on a wide range of space and time scales. The ocean does not behave like a bathtub. A lot of times people think when ice melts from, say, Greenland and goes into the ocean, that's going to raise sea level the same everywhere. And that's really not the case. So there's contributions to this pattern of regional sea level change that are different everywhere, but I want to focus on a couple big ones. So the first is natural variability and signals like the El Nino Southern Oscillation and Northern Atlantic Oscillation. So these are maps created from the satellite altimetry and showing two really big signals that were present during the record. This is focused on the Pacific Ocean. So on the left is the 1997-1998 El Nino. On the right is the 2015-2016 El Nino. And the reason why I'm pulling this out is that these signals are on the order of 25 centimeters, right? So these are very big signals, and they happen over the course of a year or two. So they go up 25 centimeters and then they come back down. So it's a really short-term burst of sea level rise that occurs. But you can see that if again, looking at the coast of California here, this sea level increase propagates up through the coast of California and really impacts coastal areas. So these El Ninos actually are a big driver of coastal flooding along the US West Coast. And there's other signals like this, these natural variability signals everywhere. There's signals like this in Europe. These changes that occur are compounding the effect of sea level rise that we see. All right, the other way that regional sea level is changing is from what we call ice sheet fingerprints. All right, so as I mentioned, when ice melts, it does not increase sea level the same everywhere. So I'm showing what we're calling here fingerprints. So these are known as fingerprints. The reason for that is maybe they look a little bit like fingerprints in terms of the spatial variability in the pattern here. It's also kind of a signature for each of the areas where we're losing ice from. So this top panel is the fingerprint for Greenland. The bottom panel is the fingerprint for the Antarctic ice sheet. So if you look at that top panel, and these blue, let me go back, these blue values are actually negative. So in the area immediately around Greenland, so where you're losing ice from, you actually get a sea level fall. And the reason for that is because Greenland is now less massive. It has less of a pull towards it. So right now it's pulling a certain amount of water towards it just because it's so massive. It has so much of that gravitational pull. When it starts to lose ice, the what water is no longer pulled as strongly towards it, and then the sea level in the immediate vicinity of Greenland starts to go down. The same thing is true for the Antarctic, right? So immediately around where we're losing ice. So here you can see, I showed previously the Western Antarctic ice sheet is losing a lot of mass. You're actually experiencing a sea level fall there. But then in the far field, so the further you are away from the source of ice mass loss, the bigger the contribution it has to sea level rise. So it's a little counterintuitive. For instance, here in the Northern Hemisphere, ice loss from Antarctic actually has a much bigger influence on sea level rise than does the ice mass loss from Greenland. Okay, and that's true where you are in Scotland, right? If you look at Greenland, you're in that blue, kind of that negative area, where actually ice mass loss from Greenland has very little effect on your sea level rise that you're seeing. And we can actually look at this. So with the GRACE observations and the modeling that we do, we can actually understand exactly where the ice mass is contributing to the sea level rise that you see. So we didn't make this assessment for anywhere in Scotland. Dublin was the closest place I could find. So just as a comparison here. So in Dublin, the contribution from ice over this GRACE time period, the last decade plus, is about 0.5 millimeter per year. And you can see that Greenland actually had a negative contribution to this. So Greenland actually caused a slight decrease in sea level over this time period. And if you look at the Antarctic, it had a much stronger positive increase. It's further away. It has this bigger separation and a bigger influence. Now, just as a comparison, I have Sydney, Australia here on the right, and you can see the contribution from Greenland is huge, right? So it's very far afield from Greenland. Greenland's been losing a lot of ice. The sea level rise associated with Greenland and Sydney is much, much bigger and very positive. Sydney is still far away enough from the West Antarctic ice sheet that it is still getting a positive contribution. So in general, Sydney is seeing a much bigger signal from ice mass loss than, say, some of these places in the Northern Hemisphere. All right, so just to kind of talk about one last process here before I start to wrap up with some slides talking about projections of sea level. Coastal subsidence is a really big factor as well. So as I mentioned, it contributes to relative sea level. So it's not just concerned with the ocean rising, but also the land sinking. And this can be due to a number of different factors. Groundwater withdrawal, where people live, they're pumping water out to use, so that can actually cause the land to sink. Something called glacial isostatic adjustment. So the surface of the earth is constantly moving up and down in response to the loading that's on top of it. So we can use something called interferometric synthetic aperture radar. And I know that's a really big mouthful. We call it INSAR. So we can actually estimate the movement of land at very high spatial resolutions. Here on the top right, I'm showing a little schematic of this. So it's a similar principle to what I discussed previously. The satellite flies over a building, a house in this case, at one particular time. It flies over that same house at another time. And if something has happened, it's going to measure that change. Hopefully nobody's living in this house. It's kind of a dramatic depiction of what might be happening in reality. That this type of thing doesn't occur. Hopefully a sinkhole doesn't appear below your house. But we can measure these changes, these really fine scale changes at really high resolutions. And this is the NISAR satellite, which is going to be launched in a couple of years by NASA, shown here in the bottom. But we have done an analysis for one particular location. So this is on the east coast of the United States, Norfolk, Virginia, looking at kind of the Chesapeake Bay region. But we can actually, each of these little speckles is a measurement of vertical land motion. And you can see some larger scale features. So you see the subsidence in red on kind of broad scales. But then there's other locations that you're actually seeing some uplift, right? So Norfolk is an area that's really affected by sea level rise and coastal flooding. So these assessments of coastal subsidence that we can make with satellites become really important. And a lot of the satellites flown by the European Space Agency are really key in making this assessment. So I talked about Sentinel 6. Sentinel-1 makes the observations that we can use to actually generate maps like this. So this kind of evaluation is being done for a lot of the coastal regions across the globe. All right, so just to kind of wrap things up and tie back into sea level on a more local level. Okay, so I work for NASA. We launched these satellites. We're really focused on providing a process-based understanding of sea level change. We want to know why, how, and how much sea level is rising. And with the observations we have available, we really do understand this well over the past decade or so. So what does this actually mean for communities at the coast? So I've kind of talked about sea level as on global scale. So we know sea level is a global problem. It's impacting coastal communities across the globe. But the impacts of sea level rise are really very local. So you have things like flooding, coastal erosion, what we call saltwater intrusion, basically the water table and saltwater contaminating freshwater supplies, coastal migration. So this is kind of natural coastlines that are shifting as a result of sea level rise. And then also just exposed infrastructure. A lot of our supply lines rely on coastal regions. Many of our airports are located very close to the coast. So sea level becomes a major issue for infrastructure and our ability to kind of live our everyday lives. So what's important now is that a wide range of these sea level processes can lead to coastal impacts. I talked about this narrowing of that safety gap. So increases in that foundation have made it such that changes in the tides, waves, winds, these natural variability signals, they can really cause sea level to become a problem and a threat at relatively short notice. So while we think of sea level projections going out to say 2100 and beyond, the problem is really a very present one for many of these coastal locations around the globe. So we need to try to integrate this information, understand these processes, and then provide this information to decision makers and planners who are living along the coast and trying to adapt or to account for the sea level rise. It's important to note that, I mean, some of these processes, tides, waves, and winds, satellites don't necessarily do that good of a job of measuring them on these local scales where they're needed. So we really need to come up with these integrated assessments of coastal impacts on a range of planning horizons. So what are we at NASA doing to help provide this, what I'm calling useful information for actual planning efforts and for generating guidance? So in the introduction, the NASA Sea Level Change Team was mentioned. I am the team lead of the NASA Sea Level Change Team. We are completely US based. So all the scientists on the team are in the US, the United States, but our interest is very global. And I'll show what that means in the next slide here. So for some useful information, access to the satellite information that I showed. So everything I showed, the data, if you go to sealevel.nasa.gov, hopefully pretty easy to remember, you can access a lot of these features, the data, the tools that we provide, and get explanations for exactly what I just covered. So it's a really good resource that we produce. Again, global in scale, it's not just focused on the US. But our team has two goals. One is to provide improved forecasts. The other is to connect with practitioners and stakeholders to try to give them useful information. So part of this is establishing partnerships with other agencies I list here, kind of the US focus, but also other organizations on broader scales, right? So one particular effort that we've taken on recently is this partnership with the IPCC. So I'm sure all of you or most of you are aware of the recent AR6, the IPCC sixth assessment report from Working Group 1, which was released at the beginning of August. So what we did as the NASA Sea Level Change Team, we partner with the IPCC to build what I'm calling a sea level projection tool. And the goal here was to allow users to visualize and download the sea level projection data from the AR6. So it's really easy access to this data. You can click on the closest tie gauge or location to your particular area in the world, get this information that's been assessed in this climate report very quickly. So it's really improving the access to that underlying information that is useful for planning efforts. And that's one of the roles that we're taking on as the NASA Sea Level Change Team. We also then, on the same portal on sealevel.nasa.gov, we're able to connect back to the observations and that other understanding and really try to create a whole package. But just to kind of show some of the details of what we provided and maybe to bring this back to your location a little more carefully to wrap up. So if you go into this tool at sealevel.nasa.gov, and you can certainly go in and do this yourself, you'll be able to find it. I have pulled out the nearest tie gauge I could find to Glasgow that's in our assessment. So this is the Millport Tie Gauge. You can click on this tie gauge, which I'm showing here. There's a variety of scenarios. So these scenarios are basically different possible futures. So there are socioeconomic pathways. Basically, how much will we reduce or limit our greenhouse gas emissions in the future? So there's a number of different scenarios that we're evaluating in AR6. here, this is just the value for 2100 for one of those particular scenarios. But if you click on that full projection link within the tool, then you pull up this information. So these are the projections for Millport going out to 2150 for each of the different scenarios. So you can see that for these scenarios, your range, say in 2100, is on the order of maybe half a meter. Going out to 2150, it starts to exceed a meter. And we can actually connect this back to those processes, because we know, again, as ice gets lost from Greenland, it's really not going to affect a place like Millport very much. So that actually lowers your projection a little bit relative to other places in the world. One note here, so the very high-end scenario from the IPCC was also assessed and included in this tool. So if we look at these really low confidence, this is kind of your worst case, you can see that sea level change in Millport could be anywhere from, say, half a meter on up to 4 more meters based on this likely range. So again, this is the worst case. I'm certainly not saying this is the one to plan for, but this is one of the ones assessed in the AR6. And then we can look at this another way. So this is basically the year by which a rise of half a meter will be reached in the future. So for the different scenarios. Right, so you can see for the higher end scenario, so it kind of goes from worst case to best case if you go from top to bottom. In the worst case scenarios, you'll reach half a meter by, say, 2080. In the best case, you won't reach half a meter by, I don't know, by after 2200. And we can look at this again for 1 meter. So on that tool, you can adjust the threshold and see exactly when you'll reach these different thresholds. I think it goes all the way from about 20 centimeters on up to 5 meters. So you can really assess the possible range and the timing of some of these events. But just as a last slide, just a comparison here. So here on the left, I'm showing Millport. On the right, I'm showing Grand Isle, USA, which is basically one of the closest tie gauges to New Orleans, a place very heavily affected by sea level rise. But you get the sense here immediately how much these projections vary, and that really is connected to the processes I talked about. So in 2100 and Millport, you're looking at about half a meter of sea level rise. At 2100 and Grand Isle in Louisiana, you're looking at almost a meter more than that across these different scenarios. So it is very location specific, and then the delivery of these projections and that regional focus becomes really key. All right, so this is my very last slide, and I've already touched on these, so I'm not going to dwell on this. Certainly, I want to leave time for questions. But I think it's important to note that sea level is a global problem. The impacts are local, and we really need to make these local assessments that are useful for planning purposes. Sea level is driven by a number of different processes that act on all different scales, from global to very local. Trying to integrate these and understand how they combine, that's really the key part to understanding what might happen in the future. And hopefully I've convinced you that satellites really do play a key role in observing these global processes and really lead to big advancements in our understanding, which then again allows us to make better projections into the future. All right, and with that, I will wrap up.
Thank you so much for that tremendous lecture. I think we all, particularly those of us in the west coast of Scotland, very much appreciated kind of bringing it home and making it really clear. I can imagine a lot of us have been to Millport and are kind of picturing what could happen. If you'll excuse the horrible pun, the questions have very much been flooding in, so we're quite happy to kind of kick off with those, if that's okay.
That sounds good.
Get through as many as possible. So Yvonne's going to bring up the first one. Started. So with a real increase in satellite traffic in orbit, so things like kind of Starlink and OneWeb, is this likely to cause problems for the work that you do?
Yes, so it's not an immediate, so let's say it doesn't impact my day-to-day activities, or it's not an immediate concern for me. There are a number of groups within NASA and other international space agencies very concerned with this and trying to deal with that problem. So it is a very important problem. It's not something that I necessarily am working on day-to-day or concerned about.
Good stuff. I think we'll move on to the next one that's coming from YouTube. Here we go. So Lindsay McLean, she works in flood risk management policy in Scotland. Fantastic presentation, I would heartily agree. She's interested to see if data could show key areas in Scotland to target flood warning services in the future.
Yeah, I think that's actually a good way to use some of the satellite data as kind of a diagnostic tool. So I kind of communicated this, that the spatial resolution varies quite a bit. So when you're talking about these local scales, I mean, it needs to make, local communities and local planners, such as yourself, certainly need to make that assessment using the tie gauges, or sorry, the satellite observations that are available in your particular part of the world. But we do kind of position these satellites as an important monitoring tool. The observations themselves, I kind of connected them to the projections, but they really tell us how sea level is changing from year to year, month to month, things like that. So I think that monitoring and diagnostic capacity is a really good use for them.
Brilliant, thank you. I think we've got another one from Astronauts. So if sea level rise is irreversible, does that mean that coastal cities will have to either relocate or even rebuild if it actually floods? And how do we make that as cost effective as possible? So it's quite a big question.
Yeah, I mean, so a lot of the sea level rise is baked in already. So what that means is even if we really do undertake drastic cuts and emissions, we're still going to see sea level. So I think it's important for coastal communities to plan for the sea level rise to occur. And there's a number of different strategies that could take place to deal with that. I think, I mean, my main understanding is in the US, in some parts of the US, we are starting to see retreat from the coastline. So coastal retreat is being used as a solution. In other parts, so I showed Norfolk, Virginia, they're raising houses, they're raising roads, things like that. So finding ways to live with the sea level rise that's going to occur rather than abandon. That assessment really just has to be done on a local level. So what is cost effective for a particular region? What is the best solution given the potential increase in sea level? That's a really good question, a really big question. And what NASA is trying to provide is really the information, the data to try to make those decisions.
And that's what the kind of predictions that you're making can be used for, I suppose.
Exactly, yeah.
Brilliant, thank you very much. I think we've got another question coming up here. So Florence has asked, have you seen satellites improve dramatically over the last 3 decades in the same way as, say, medical technologies have improved?
Yeah, so that varies depending on the particular technology. So the satellite altimetry, the core observation that we're using in 1992 is similar to what it is today. There have been improvements, so our observation is better now. Some of the tracking we do, the uncertainty on that measurement, but the core principle is similar. On the other hand, like GRACE and GRACE follow-on, right? I mean, that's a relatively new technology. It didn't exist before the launch of GRACE. It's a completely new idea. So we're seeing those changes that have occurred over the past decade, and there's new ones coming up. So there's the SWOT satellite, the Surface Water and Ocean Topographer satellite that's going to launch next year. Completely new technology, and we're going to have really high resolutions of sea level measurements from that. So I think there's continuing advances and new satellites that are coming online, new technologies to fill in gaps in our observational network.
That's exciting. We'll keep an eye out for SWOT launching.
Yeah.
Thank you. So I think we've got another one. So that's quite a good question. Claire has asked, can changes within the Earth's core influence sea level?
Yes, so I would say I don't at all study kind of that solid Earth processes. I think the important thing to consider that within the timescales we're talking about, we understand the processes that will make the big changes in sea level, right? So anything that happens elsewhere is going to pale in comparison to what we're seeing in terms of like changes in ocean circulation, ice melt, and things like that, especially in the timescales that are relevant to us now from a planning horizon perspective.
Okay, so we're really looking at kind of surface changes rather than anything deeper.
Yeah, I mean, it's really a relative thing. I mean, there are a lot of processes that do affect sea level in different ways. Some of those are natural signals that you expect to go up and down on very different timescales. But yeah, it's when you're talking about some of these coastal impacts, again, it's the ones that are on the same timescale as these planning horizons of, say, I don't know, 10 to 100 plus years, something like that, which most coastal communities are worried about.
Okay. I think we've got a question coming in from Facebook here. So Nicole has said that they thoroughly enjoy your presentation. Fully agree again. So are there any future missions planned for hyperspectral imagers for the monitoring of coastal habitat degradation? Try and get my words out. And on another note, how can we as scientists help bridge the gap between science and policy regionally and or internationally?
Yeah, so the answer to the first question is yes, but I'm not as aware with what's happening with like the European Space Agency and their immediate plans as I do on the NASA side. So I probably won't go into too much more detail either than to say yes, that is a focus in kind of looking at these these coastal zones, and exactly that, the habitat degradation, some of this coastal migration, these natural habitats, and how their ecosystems and how they're varying. On the other hand, so that's a really important question, one that I've become really involved with on the national level here in the US. We talk a lot in the US about co-production, co-development. So basically working with practitioners, what I'm calling practitioners, having scientists directly engaging in that, having funding mechanisms from these large agencies that actually target that co-production. So in the US, it's very much a work in progress. How do you get scientists and practitioners in the same room with funding to actually do something? I don't have a solution other than to say I personally am working hard on that and trying to kind of bridge that gap. And I think there's a lot of importance to that, a lot of societal relevance. So to the extent that other scientists can kind of jump in and do that, I think is certainly a good thing as well.
Yeah, I very much agree. That was a brilliant question. Thank you for that. So this is, again, I suppose maybe where the public can get involved. So are there any citizen science projects that the public can get involved with regarding sea level changes?
Yep. So I mean, I apologize for this being very US focused. It is where I am, but I mean, here in the US, there's a number of different initiatives that citizens can get involved with in these sea level science projects. So from a satellite perspective, we make these big global measurements, but we don't always have what I call the in situ or really local measurements. So there's a number of different efforts to, I don't take pictures of how coastlines are changing over time. So there's like particular areas, if you go to a beach town, where people can go and have a snapshot, then upload that, right? So and that buildup of that record really does help us as scientists. In other locations, there's opportunities to install water level sensors. So if you have a dock and you're attached to your house or you have access to water, installing those things, all of that is really important. I would also say, so a lot of planning is done on a very local level. So there are community planning efforts, getting involved in those, understanding the data and what's happening in your particular area. In the US, voting matters a lot, right? So becoming informed and actually voting with an understanding of the underlying science is a really key aspect that we're trying to address here in the US as well.
Yeah, I would definitely say that applies to the UK as well. So thank you very much for that. I think if there's any sort of websites like the Zooniverse and things like that here in the UK, and in fact can be accessed globally, which are well worth having a wee look at too.
Right.
I think we've got another question coming in. There you go. So astronauts, as a student in Scotland, what would you say you want us to do to advocate sort of what it is you're talking about, and what are some technical innovations that would help this?
Yeah, so I mean, to advocate for, I guess the way I'm interpreting that question is how do you advocate for having the sea level science that we have integrated into adaptation planning efforts? I mean, how does the public support that? Again, voting is a really key part of that, being informed as to what is happening and having that science-based understanding. I was previously, before coming to JPL, a professor at university and taught kind of these big climate change classes to introductory students, first year students coming in. And it's really just to inform, make them literate in these subjects so that they can then either pursue this as a passion, maybe they want to go into climate science, but just in general, being informed and making good decisions and pushing community leaders to actually make these changes. I think that's a really key piece. Maybe to answer the question a slightly different way, studying climate change is really interesting. My background is in aerospace engineering. I'm not a climate scientist or a physicist, anything like that, but it's a really interesting problem. The technology and the connection to the science is really interesting. So for anyone who does have an interest in kind of pursuing this field of study, I would definitely encourage it. It's something that I never find boring.
Right. And I think your comment about scientific literacy, I mean, the last 18 months have proved kind of how important that is. So yeah,
Right.
and I think particularly with climate change, it's crucial. I think we've got one final question coming in. So I suppose quite topical for us, particularly here at the Science Centre. So what for you would be the ideal outcome from the upcoming COP26?
Yeah, I'm going to answer this from the perspective of a scientist. And I think that having these conversations and finding ways to reduce confusion, redundancy, and increase collaboration between different agencies, different countries, and the science that gets shared. I know here in the US, we have the NASA Sea Level Change Team. In the UK, there is a science team that is doing something similar for the UK. increasing the coordination across these different groups of scientists, I think, would be really important. I'm trying to take lessons learned. I mean, there's a lot of stuff we could learn from the group in the UK doing this, and I'm sure vice versa. So really having those opportunities and encouraging increased coordination on the science level, I think would be something really big. More as a citizen of the Earth, I think, I mean, whatever we can do to reduce greenhouse gas emissions, that's really the key. Everything I talked about, I talked about different scenarios, that foundation of sea level. To the extent we can keep future sea level rise down, everything I presented would be much more optimistic, right? Any of those coastal flooding, it would just be that much better for the future. So hopefully we can really, again, start to keep making headway towards reduction of greenhouse gas emissions.
Yeah, I think we're hopeful for that too. I think there is always something to be optimistic about in all of this. So I think that is the final question that we've had in. So it's just up to me to say a huge thank you to our audience for joining us tonight. We had quite a few people viewing the stream, and just to say an enormous thank you to you for joining us from all the way from Southern California. It's been absolutely tremendous. We do have a few more David Elder lectures coming up, so please do, if you head to our website, sign up to the planetary mailing list. We'll be able to keep you informed on those. Of course, we would like to get your feedback on this lecture, so we're going to drop a little link to a survey in the chat, so if you could give us a few moments just to fill that in, that would be tremendous. But just to say a final massive thank you to Dr. Benjamin Hamlington, who's joining us all the way from NASA. Thank you so much.
Thanks a lot. Appreciate it.